I was yesterday. Now it was.
Again, 9, 10 km.
Sorry, what do you mean?
Hello, everyone. Welcome to the lecture 2 about the coefficient ring of the final local ring. The main objective of this lesson is to prove the existence and existence of a final local ring R0 with maximal integers MR0 such that R0 is a subring of R. R is a final local ring with maximal integers MR and residual field FQ with Q is P power R, P is the prima, R is the positive integers. R and R0 have the same residue field. And integer and maximal integer, the maximal integer of R0 is the intersection of maximal integer of R and R0. I explain that let us let the R is a finite local ring. Final local ring is a ring with only maximal integer. Maximal integer of R is denoted MR, the maximal integer of R. FQ is the residue field of R. FQ isomorphic. This is the field because MI is the maximum. The main objective of this lecture is to prove existence and uniqueness of R0 such that R0 is subring of R. R0 is local. Residue field of R0 is isomorphic to residue field of R. MR0 is the maximal integer of R0. Finally, maximal integer of R0 equal maximal integer of R intersection with R0. We call R0 coefficient ring of R. This is the main objective of this code. Let us continue. When we, as there is the local ring, MR is the maximal integer. We have the reduce modulo MR. Okay. P is the canonical map. When we have the element of R, the reduce is x plus maximal integer of R. We can lift any element of final FQ. There are many ways to lift this element. Explain this. Explain this. By some example. We take Z4, Z4, the maximal integer of Z4 is set 02. The residual field is F2. When we have the reduce is 0. Reduce for 1 is 1. Reduce for 2 is 0. Reduce for 3 is 1. When is, for example, 1, we lift maybe by 1 or 3. The lift, the 1 are 1 of 0, we lift 0 or 2. This is the lift, it's important to the circle. Continuous. Okay. The canonical map P, we can extend this map to polynomial ring Rx. From polynomial ring Rx as the follow, with the standard coefficient by coefficient. When we have a polynomial of what if the element of the polynomial ring Ax, the image by P is PF definite by as bar R0 plus bar R10 plus dash 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 plus RD plus bar RD x power D. We explain that by this example. You take Z4, polynomial ring over Z4, polynomial ring over Z4, 2 polynomial ring over F2. For example, we have this polynomial x power 4 plus 2x power 3 plus 1 image 3 P3 x power 4 plus P2 x power 3 plus P1. P3 égale 1, P2 égale 0 and 1. The reduce of this polynomial modulus 2 égale x power 4 plus 1. This is the reduce. The lift of this polynomial, or lifting of this polynomial is here. Is a reduce. Okay. It's a reduce. It continues. We know that there are several lifts of the polynomial, but there are one reduce of the polynomial. Okay. They are the important definition. When you take two polynomial over two polynomial, one is in one, we let the f a polynomial in Rx and G a polynomial if Fq X. We say G is free, G is a square free. If G has no repeat irreducible factor in this factorization. F is the lift to Rx of G if PF ou bar F, PF égale D. J is the reduce, F is the lift. F is the primary if PF is the power of an irreducible polynomial over Fq. F is unit if PF is a non-zero element of Fq. F is regular if PF is different to 0. And finally, F is a zero divisor if a PF is equal 0. For example, we take F equal 3x squared plus x plus 1, H equal 6x plus 4. Two polynomial over Z9. We have Z4 plus 6x plus 3 is the primary. We explain that is the primary. It's the primary because the reduce modulus 3 is the power of the irreducible polynomial. It's the irreducible polynomial. This polynomial is x. X is the irreducible over F3. F is the regular because PF PF equal x plus 1. X plus 1 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 plus H is the unit. If F is unique because reduce of H equal 1. The polynomial free x squared plus 6x plus 3 is a zero divisor because the reduce of this polynomial is equal to 0. The last example is important. We have f is the coefficient the leading term is 3. 3 is the zero divisor in the ring Z4. 3 in the ring Z9, because 3 times 2, 3 times 3 square, 3 square reduce 0 in this ring. When a polynomial f is not monic because coefficient leader term is 3. 3 is different to 1. Note that f is the regular because f reduces to the polynomial x plus 1. When is the regular polynomial, we can when is f is the regular polynomial, then there is a unique polynomial h such that product h by h equal a monic polynomial. Explain that. Okay. Okay. We take ring Z9. Polynomial ring over Z9. F is 3, S equal 3, X power X power 3x squared plus F equal difference of 0. F is irregular. F is not monic. There exists H in Z9X such that FH is monic. This polynomial H equal H equal 6x plus 4. 6x plus 4. We check it. H we extend it 3 times 6 equal 18 x power 3 plus 12x square plus 6x square plus 4x plus 6x plus 4 modulus 9. This is 0. 12 plus 6 equal 18. 18 modulo 9 equals 0. 4 plus 6 equal 10 plus 4. 10 modulo 9 equal 1. This polynomial is monic. Okay, in the follow, in this lecture, any polynomial is the monic, because when is place, sorry. Okay, we call that in this ring, for example, we call that, or take in this ring, this polynomial is the unique because okay, this polynomial is the unique in this ring. Okay, in this lecture, any polynomial is unique because if f different 0, they exist h a f well, where f r is the final local range. Okay, we can we can we can we can find x in this polynomial. X, you can find h in this polynomial. H is a unique such that f h is a unique. F pf different 0, by definition f is regular. In this ring, any polynomial is either unit or regular. Okay, we can continue. Okay, proposition, let the f be a regular polynomial over R. R is a final local ring. Then there is a unit polynomial H over R such that FH is the monic. Okay, lemma said that this is the result to prove the Hell's lemma. let f1 and f2 two polynomial over R. Then the polynomial, the integer generate the sum integer generated by f1 and f2 are coprime if and only if integer generated by p of f1 and p of f2 are coprime. The proof in this equivalence is obvious. It's obvious. Okay. You use is the views. You can see, you can write a sketched off a proof. Okay. F1 and F2 in Rx, PF1 and PF2 in FQX. FQ is the residual field of R. Let me say that F1 integer generated by F1 plus integer generated by F2 equal Rx if and only if integer generated by F1 plus integer generated by F2 equal FQX. Okay. There a okay. This sense étoile says the étoile says there exist H1, H2 in Rx such that H1 F1 plus H2 F2 equal 1. We use the redux. We use the canonic map P redux. The redux we have PF1 please sorry PH1 PH2 plus PH2 PF2 equal 1. This proof that PH1 polynomial generated by P generated by PF1 plus PF2 equal FQX. This means integers generated by PF1 and integer generated by PF2 are coprime. The inverse sense, we leave the inverse sense in this proof and in exercise. Okay. Use this result to establish the Helsel lemma. Helsel lemma said that when Helsel lemma said that for all monic polynomial f over R such that PF equal J1, J2, where J1 and J2 are co-prime monic polynomial over FQ. Then there are F1, F2 monic and coprime over R such that F equal F1, F2 and J1 equal F1 et J2 equal P of F2. Okay, I explain. Ok, le seul lemma. F is the polynomial over A such that PF equal G1, G2. PF is a polynomial over FQ with uh, J1 and J2 are coprime. I coprime. F is monic, J1, J2 are monic. Then they are F2, F1, over R such that F equal F1, F2 with P F I equal P J I. I is 1 or 2. And F1 F1 and F2 are coprime. Coprime. Okay. This lemma is important to factorize a polynomial over R. You explained that for this example, we have this polynomial f equal x plus 8 over z9x. Pf equal x minus 1 plus x minus 1 products of x minus 1, x plus 1 over z3x. This is G1, this is G2. Okay. here, this is F1, this is F2. J1 et J2 are coprime. The lift F1, the J lift F1 and F2 are also coprime. We see that here. Okay. Okay. Factorization of the monic polynomial over R is given by this theorem. Let f be a monic polynomial over R of degree greatest than 1. Then there exists pairwise coprime monic primary. You recall that a polynomial is the primary if it's the power of an irreducible polynomial. It's the primary polynomial f1, f2, dash, 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 fu over R such that f is the product of f1, f2, dash, 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 fu. If there are other factorization by h1, h2, dash, 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 hv, as the pairwise coprime polynomial primary over R, then u equal v. They are the same. They are the same monic primary polynomial. This factorization is uniqueness up to permutations. We say that the polynomial over R is unique factorization ring. Unique factorization ring. We explain this concept, unique factorization ring. The first lesson, we define unique factorization domain. It is well known that the polynomial over field is the unique factorization domain. To see today, the polynomial over finite local ring is a unique factorization ring. Unique factorization domain, for example, FQX, unique factorization ring. For example, Josier, what is P is the not primary function? P, son, you explain that, okay. Okay, P is the important definition. P, you answer to question of Josier. P is a ring epimorph. P is the ring epimorph. P is the ring is the epimorph. It's the epimorphism of the ring. You explain that. Okay. P from R to FQ. X plus maximal integer. For example, Z for FQ. X plus x plus maximal integer. Maximal integer is 0, 2. This is the ring. This is the ring. The field is the ring. With this property, any non-zero element is the unit. This is the ring. P is the ring. P is A. P is the A ring. AP more is Px plus y equal Px plus P2. Px, okay, and P1 equal 1. Here, element of Z4, 0, 1. There are no 1 in this maximal ring. 1 is 1. 2 is reduced, is 0. 3. 3 equal 1 plus 2. 3 est réduit à 1. Donc, P is the ring epimorphism. It continues. It continues with okay. Unique factorization domain, for example, FQX, unique factorization ring. For example, the polynomial, the polynomial ring over R. When is take F element is this ring, F a monic, you use reduce P, you obtain F. PF is the element of FQ, or FQ, or polynomial over FQ is the unique factorization domain. For that, PF equal G1, G2 plus GU. By definitions, we can lift any element by Russell lemma. By Russell lemma, we can lift any GI. We obtain F1, F2 plus FU, such that GI equal P of Fi. I go from 1 to up to U. This is the mechanism of factorization of the unique factorization ring. We use the Russell lemma to lift any J-ith. J-ith is the polynomial of the FQ. Okay. This you explain by this picture. F is monic polynomial over R. Rx is a unique factorization ring. We use P, we obtain F, we obtain a PF. PF is the element over FQ. FQX is a unique factorization domain. So that FP can be factorized into into power of irreducible polynomial over FQ. Ji are pairwise coprime monic irreducible polynomial over FQ. This factorization is unique up to ordering. You use the lefting to obtain the factorizations over R. And for that, you use a lemma, you use a Helsel lemma. Helsel lemma authorizes to lift, to obtain F1, F2, dash 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 FU. F is products of Fi. These products are unique up to ordering. Of course, P P of Fi are pairwise coprime. Okay. This is the mechanism of factorization. This is the mechanism, the factorizations of any monopolynomial over final local ring. Okay. We have definitions. The basic, you let F a polynomial over R. F is the basic irreducible over R if PF is irreducible over FQ. F is the basic primitive over R if the PF is a primitive over R. The first lecture, we talk about the irreducible polynomial and primitive polynomial. A primitive polynomial is primitive polynomial over FQ is an irreducible. The primitive polynomial is an irreducible polynomial if a root is the primitive element of the unique group of the FQ. Explain that. Explain that. Okay. We take FQ, a final field. FQ is a group of unit. Of FQ. We see that FQ time is circle. And generator of this is called the generator is called the primitive element. Alpha is a primitive element of FQ if alpha is the generator of 1 alpha square dash 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 alpha power q minus 2. Okay, it's a primitive element. F is a primitive polynomial, is the primitive polynomial over fq if f is a minimal is the minimal polynomial of a primitive element over q. Alpha is the primitive element. Okay, well, this is the definitions of primitive polynomial. Basic irreducible polynomial and basic primitive primitive polynomial. Is okay. We explain this definition. R is the local ring of reducible field. P is the canonical map. Okay. If you take f a polynomial over R, f is a basic irreducible polynomial over R. If f is irreducible over irreducible over fq. F is a basic primitive polynomial over R if Pf is a primitive polynomial over fq. This is definition. We take some example. Okay. For example, this remark stand for example, remark in the ring is the polynomial ring of the local ring over a local ring R. We have any basic irreducible polynomial is also irreducible. This means a basic irreducible is a strong concept. Is a strong concept. However, the converse is false. For example, we take x equal x square plus 2x plus 3, a polynomial over Z4. This polynomial is irreducible over Z4 because there exist no element A and B over Z4 satisfying this product, satisfying this equality. But the reduce is irreducible. Okay, this example of the polynomial is irreducible over Z4, but it's the not basic irreducible over Z4. We can see that the reduce of f is the square of the irreducible polynomial. This polynomial is x plus 1. Donc, we note that any basic irreducible polynomial is irreducible. The convex is false. Helsel lift. What is the Helsel? What does Helsel lift? What is the Helsel lift? Helsel lift is for defining the Helsel lift, we need in this lemma. Lemma say that for all possible integer d, there is a monic basic irreducible polynomial of degree d over r divided x power q power d minus 1 over r. Okay, there exists. This existence is this existence unique? When can the unicity of existence is this existence is the unique. Theorem establish unicities of this existence. We define Helsel lift by f is a Helsel lift of J to R if J is reduced of f and f divides x power n minus 1 over r for some positive integers. Okay. Theorem: J has a Helsel lift to Rx if and only if Pj is square free, then Pj has not square factor. Square free means that Pj has not a square factor. Has not a square irreducible factor. And constant term of J is different of 0. Moreover, Helsel lift to Rx of J is unique if it exists. Okay, the concept of Helsel lift is important to factorize the monopolynomial over a final local ring. Okay. We explain this lemma. Okay. In the first lesson, we established that if your J is a polynomial over FQ, J is monic and T is the monic and irreducible over FQ. Okay, degree of D equal D. We have this theorem. D divide x power q power m minus x if and only if J, if and only if degree of J divides T. Okay. This lemma says that for any monic basic polynomial of degree D over R, they are there is a monic, there exists a monic basic polynomial of degree over R divides x power q power g minus 1 minus 1. Okay. Here and here we use the Hessel lemma. Hessel lemma, we lift J. J we lift is F. PF equal J. F is the lifting of J. J divides this polynomial. This explains that this is a consequence F divide FQ FQ M minus and PF equal G. This is consequence of Hessel lemma. Okay. Oh, sorry. M here. Okay. Degree of D equal degree of F. Because PF equal G, F and D harmonic. Degree of F equal degree of J equal J. Okay. Here, J divides this polynomial. Hessel lift allowed us to obtain F divides this polynomial in this range. You see F divides this polynomial of this range. Okay. Oh, okay. Definition establish the concept of Hessel lift. This F this f that is a lifting of J equal Helsel lift if f divides of some x power n minus 1 over r. You explain that is important for the circle. We take example. In Z9X, we take f equal x square plus, non, sorry, Z free, we take J equal Z square plus X plus 2. Okay. J divides this polynomial in this ring. The lift of J has the several lift. For example, we take H for the lift of the one. Okay, we have F Z free. That is the field FQ. The lift to Z9 H free 0, 1, 2. The lift of 0, 0, 3, 6. The lift of 1, 1, 4, 7. The lift of 2, 2, 8, 2, 5, 2, 5, and 8. The reduce of 0 is 0. The reduce of 3 is 0. Modulus 3. The reduce of 6 is 0. Percent. The reducer of 1 is 1. The reducer of 4 is 1. The reducer of 7 is 1. The lift J has several lift. For example, H equal 4x squared plus 7x plus the lift of 2 maybe. H is a lift of J. Another lift, 7x squared plus x plus 8. Oui, plus 8. This is another lift of J. Especially the Hessel lift is the particular lift of the polynomial. The Hessel lift of J is the lift. Verify this verify this. J must divide x power q power d minus s. Here, q égale 3, d égale le degree of 2 is 2. Donc, d divides minus x. We come in, pardon, sorry. It's not D, it's F. It's not D. F. F is V, because F is unique. It's unique. It's the Hessel lift of J2 Ax if PF égale J and F divides x power q power d minus x. D is degree of J, and q is the cardinality of the residual field of R. You recall that F and J is harmonic. Okay. For example, F égale x square plus 4 plus 8. Yeah, it's unique. Questions. How to compute the Hessel lift of the D? We give the algorithmic. Math gives Hessel lift for the polynomial over Z P power K. This algorithm, we require input, we input the polynomial divides x power n minus 1, where P is the prima coprime with n. We find the Hessel lift 11k. This is a polynomial. We write a set program to compute to compute any monic polynomial, any Hessel lift for monic polynomial over zk. Okay. If we can send the search program, you can send the search program after of this school. Okay. We write some example. If at the time we use the program to compute some lift Hessel. We write this example. Okay. in FQX, we can decomp factorizations into pairwise coprime irreducible polynomial of this polynomial is x plus 2 times x plus 1 times x squared plus 1 times x squared plus x plus 2 x squared plus, okay. The Russell lift in Z9 of this polynomial is here the lift we obtained by same polynomial, the lift we obtained by same polynomial, the lift we obtained this polynomial, and the lift we obtained, okay, here you are in this range. Okay. Any factors here, this is the basic irreducible polynomial over Z9. Okay. Use the Russell lift. To Z9 to lift this polynomial obtained x plus 8 and so on. Okay, you answer to questions of main objective of the lesson. For that, the causal ring of the final local ring verify this condition. We recall this condition. Recall this condition. R is a final local ring. MR is its maximal integer. FQ is residual field. Okay. Yeah, we ask this question: is there R0 final local ring such that R subring of R, second, residual field of R0 is isomorph to FQ. Finally, maximal integer R0 equal maximal integer R intersection with R0. This maximal integer equal P R0, where P is the characteristic of the residual field of R0. Okay. Is there R0 such that this, and this? The answer is yes. This R0 is the Galois ring. Definitions. A Galois ring R is the final local ring satisfies the maximal integers is the form PR, where P is the characteristic of its residual field. That is the definition of Galois ring. Galois ring is the final local ring such that its maximal integers in the form PR, where P is the characteristic of the residual field of R. We recall, we repeat. I repeat and repeat that, and repeat this definition. A Galois ring is a final local ring such that its maximal integer is generated by its characteristics of the residual field. Okay. The following theorem give the existence and uniqueness of Galois ring. The Galois ring exists and uniqueness. Okay. To construct the Galois ring, we need a basic irreducible polynomial and we need a ring of integer modulus PR. Okay. We explain that. Explain this by okay, Galois ring. Galois ring exist. Yeah, uniquely. Galois ring is unique if there exists is unique. R0 is the Galois ring if it's isomorphic to Z P power A X F H, where H is a monic basic irreducible polynomial over Z P power A. That's established the existence of Galois ring. Existence is due. Existence is the consequence of existence of the monic basic irreducible polynomial over ZP power A for any degree of this polynomial. Uniqueness. For any ZPX, this quotient ring is isomorphic to this coefficient ring H prime, where for any monic basic irreducible polynomial over ZA of degree the same of degree h égale h percent degree. Donc, for any basic irreducible polynomial h prime, for any monic basic irreducible polynomial h prime over zp power a of degree h prime that is equal to h to degree to h. This we have this isomorphic. Its consequence is a uniqueness of Galois ring. For that, we denote Galois ring. For that, we denote okay. As A0 the characteristic of R this is a monomorphism of ring that is a monomorphism for ring since P power A is characteristic of R0. It's characteristic of R0. Here is the residue field of R0. Existence à uniqueness of Galois ring of characteristic P power A R is degree of H. Here, this is characteristic. Okay, We repeat this. Okay. A, A is isomorphic to this quotient ring. H is a basic irreducible polynomial over ZA. We have this notation, denote the Galois ring by this notation. P power A is the characteristic of the R0, and sorry, here is D. D is degree of basic irreducible polynomial. Okay, let us continue. Okay, explain that let H be a monic basic irreducible polynomial over ZPA of degree R. Let alpha equal X plus integer generated by H. Obviously, alpha is the root of H, and ZPA of alpha in bracket is the free ZPA module over ordering polynomial basic. Moreover, we have characteristic mean that this ring inject in Galois ring. A final residue field of the Galois ring, this ring is project to residue field. We note that JR Galois ring of characteristic PR of rank R. R is the degree of the monic basic irreducible polynomial over ZPA. Okay. The main objective of this lecture attained, the coefficient ring of a final local ring is R0. R0 is the unique up to isomorphism is the unique, exist is the unique. Okay, one is ideal of the coefficient ring. What is the ideal coefficient ring? R is the final R is the final local ring. R0 is the Galois ring, coefficient ring of R. R can be write as the quand on review of the polynomial of the set of polynomial over R0 of indeterminate theta 1, theta u, where theta 1 is the minimal form, is the minimal generating set of his maximal integers. Okay, the x is the element of R if x is the sum of A1, A2, dash, 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 AU, 1, K1. Okay, we can write any element of a final local ring on this sense where R1 dash 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 RU in the element of Galois ring. Done is in this main integers behind the coefficient local ring of the final local ring. It become continuous. Okay. What is a Lorentz invariant of the local ring? Let theta 1 dash 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 theta v a minimal generating set of the maximal integer of R. We have the chain of these integers. Since R is the final, the chain, there exists the integer s is called the potency index of integers m. Okay, we have this s triple v0 dash 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 v x minus 1. This s triple are called the Lorentz invariance of R, where Vt is dimension of this vector space, or this vector space. Then the number V equal Vt. Example, we take R is the final local ring defined by Z2 UV. U square equal U, 2 equal UV equal 0. You determine M square equal 0. Donc, so that Lorentz coefficients of this ring equal couple of 1, 2, couple of 1, 2. Nilpotent index of this ring equal 2. This is the lattice of the integers of this ring. This ring has eight element. The element of this ring can be write of this can be write on this form. Okay. R, for example, R, U, V. U square égale UV square égale UV égale 0. Okay. The element X is the element of R if X égale F0 plus X1U plus X2V, where X0, X1, X2 is element of F2. Okay, so that R is isomorphic to also vector space over FQ. Okay. Cardinality of R equal is 8. R has 8 elements. Okay. R has 8 elements. Okay. Okay. The importance of a Lowy coefficient of the final local ring. The Lowy coefficient belongs to determine the cardinality of a final local ring. The cardinality of the final local ring equal Q power V0 plus dash 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 plus Vx minus 1. For this example, the lowering invariant is the couple 1, 2, 1, 2, 1, 2. Okay. V0 equal 1, V1 equal 2. The Lowy invariant is the couple 1, 2. Okay, the cardinality of ring in our example equal Q power this sum. Power this the sum. Donc, cardinality Q is the cardinality of the residue field. Q is the 2. Okay, so that's Lowy invariant is here equal 8. This is how to compute the cardinality of the final local ring. Okay. Item 2 of this proposition, R can express Galois ring. Any element can be written as the multivariate polynomial over coefficient ring of the R. The indeterminate are the element the indeterminate of this ring is form the minimal generative set of the maximal integer of R. Okay. We continue with technical set of the local ring. Technical set of the local ring is the set of root of polynomial x power Q minus 1. Technical set. Technical set Technical set. Technical set of R, which not by is a set of elements of R such that x power q equal x. Q where FQ is the residual field of R. Okay. Okay. This is a set. This is a technical set. When you move 0 in this when we obtained minus 1 equal 1. This is the subset of unit of R. We prove that this subset is the subgroup of the unit group of the group of unit of R. And this group is cycle. Is isomorphic to a proof. This is important. Is isomorphic to this group. Okay. The consequently of this the description de P to is isomorphic. Isomorphism of groups. Mean that any x in R, there exist x0 in Technicolor such that px equal p0. This means x equal x0 plus maximal Indian. No, that is not correct. It's not true. Okay, x minus x0 belongs to maximal Indian of R. That is important to periodic representation of element of a special unit. Okay. Continues. The element of the Technicolor set are the root of the polynomial x power q minus x. When is move 0, 0, we obtain ternary set star generated by alpha. This group is isomorphic to the subgroup of the residue field FQ. Ok, je lui explique, these 3 points. It's important to construct a Galois ring. To construct a Galois ring, the Galois ring R0 alpha as R0 Galois ring. Okay. Alpha is the F is a monic basic irreducible polynomial over ZA. Okay. We add the F divine x power p power degree of degree r or degree power r minus. Okay. F is the basic polynomial divine this polynomial. Et alpha, oui, alpha the groups generated by alpha is of order p power r minus 1. That is, sorry, F is the basic, F is the basic irreducible, but F is the basic primitive polynomial, primitive polynomial. Okay. To construct a basic, to construct a ternary set, we need a monic basic primitive polynomial. We repeat, to construct a ternary set, we need a monic basic primitive polynomial. Okay. Okay. To generalize the Frobenius automorphism, we take alpha a generator of ternary set. This map to alpha associate to Saint alpha power p is the automorphism fixing the element of this ring. Fixing any element of maximal integer and fix any element of integer is a ring of integer modulo p power a. Okay, Galois extension of the local ring. A local ring, we take two local rings. S is the Galois extension of R. If S equal R alpha, where alpha is the root of the monic basic irreducible polynomial. Ok, je explique this. Explique. Simple. S is the Galois extension of R. S R Galois ring AM R0 Galois ring. Ok. Is a Galois extensions if S equal R alpha, where alpha and F is monic, basic, irreducible. Beta, we take irreducible, primitive, polynomial over ZPA of degree M. Okay, this is the definition of a Galois extension. We need the basic primitive polynomial over Z PA of degree M. M of degree M. Ok, bon, je laisse au recrassement. Bon, a special class of the final local ring. This a special class is called final chain ring. Final chain ring is the particular final local ring. The final chain ring is the local ring whose integers are principal. Integers are principal. Okay. We obtain these representations of element in the final chain ring. This representation is called periodic representations. Okay. Oh, you explain that quickly. Final chain ring. R is a final chain ring. If R is a local whose maximal integers is principal. Okay. maxima integer is a principal. We have addition A, maximal integer, dash, dash, dash. AM, where theta is the element of maximal integer does not belong in this integer. Okay. Theta is the generator of maximal integer because maximal integer is a principal. Okay. Okay, tomorrow you finish with this lesson and start lesson 3. We need to understand the final chain because any corrected code over ring, we take we take final chain ring as example to construct the corrected code. Final chain ring is important. It's a very important to construct the linear code over ring. It's very difficult to construct the code over non-chain local ring. It's very difficult. You see that on lesson 4, last lesson. Thank you a lot for your kind attention. See you tomorrow for lesson 3. Tomorrow,
Okay, thank you.
tomorrow you continue. Tomorrow you finish with second lesson by constructing of the final chain ring. It's important of the second of this lesson. Thank you very much for your kind attention. There are any questions? Okay. My mail, you send.
Yes, please send the PPT.
Email.
Yes, please send PPT.
Please.
Send the PPT, PowerPoint present.
Okay,
The
okay.
present.
My slide. Write me in the address mail Alex FOTUE @gmail. Okay. Oh, okay. Alex FOTUE gmail.com. Gmail. Yes. Code. Okay. You write the address mail. Okay. My address. Okay. Okay, thank you very much. See you tomorrow.